Then I'll try to show, again, just basically how we tie geology to seismic. After that, I will show some example of seismic data structures. After I finish my presentation, I think the most fun is going to start. I'll try to show my thesis data by using Petrel. Interactively, we can interpret horizon faults. We can go through this seismic data in 3D view and 2D view. And also, I will ask a question about in around end of the presentation, so we can answer in I think in conversation part. So let's start. Doing seismic interpretation means different things to different people. We can interpret few 2D seismic lines. Integrated grids of 2D seismic lines covers really huge area to understand the potential of the area. Then we can combine this 2D and 3D seismic survey and work together. Also, we have some small 3D survey, especially onshore area, and we have some large 3D survey on offshore area. So we can interpret all of this kind of seismic data in our study. And to interpret seismic, this is a basic schematic interpretation workflow. First of all, as you know, I'm working on a petroleum industry. So my purpose of this interpretation to discover oil. So we can ask a question for ourselves: can seismic data help? If the answer is yes, we can check other data, seismic data and well data. We can create our common database. Then we can tie, if we have well data, our geology to our seismic. And we can make structural and stratigraphic interpretation. So we can, after that, we can do some rock physics, rock properties prediction. Then we can make a decision to well data or not. But to do seismic interpretation, we have to understand how the data are acquired and processed. It's pretty important. I'm not going to cover very detailed acquisition and processing sequence, but I will show some examples. The main idea of this presentation make you more awareness about seismic interpretation. After this presentation, you can understand that oh, I have to know this and this to make seismic interpretation. Also, seismic interpreter is going to face some problem, some geological problem, some dimension orientation, and some other image problem. Also, after we understand acquisition and process, we have to understand their relationship about seismic data, on seismic data. And also we have to understand how we display data, seismic data, and how we analyze this. And of course, I mentioned about well tie. We have to tie our data set to real geology. And seismic interpreter could be geologist or geophysicist. Both of them commonly undertake seismic interpretation. And in industry, geophysicists tend to be pay finders. What does it mean? People who focus on quantitative methods to directly detect hydrocarbon. And also geologists tend to be a play finder. And what does it mean? It is a structure, construction, the positional histories. These are after that, these two concepts is going to combine, and we can make final decision to drill well and find oil. But if you are geoscientist, your background geophysics, for example, your background is geophysics, and you can improve yourself in geology. or your background is geologist, but you learn lots of things about geophysics, you can call yourself as a geoscientist. And geoscientists can have idea and can do both payfinders and playfinders together. And let's start to seismic acquisition and processing. I sometimes repeat myself because these are important. To interpret seismic data, we have to know history of data. What kind of geology we are going to deal with in our study area, what is our acquisition parameters, what is our fault size, record length, bin size, sample rate, what is our processing parameters. These are just basic and main topics. There is lots of topics, and you are going to see in the future slides. What is our migration, what is our data polarity, what is our resample rate, and also we have to check other data sets, wells, field geology, gravity, and magnetics. And this is basic seismic acquisition diagram. We can call this a onshore 2D acquisition schematic diagram, and this is the marine 2D seismic acquisition diagram. And basically, we have a source here, and after this source create some wave. They reflect on subsurface or inside the earth, and these reflected waves listened by these hydrophones, and by doing this, we can image under the earth. Then we can create a seismic. Before I move more, let me explain something. This is pretty important. When you let's look at here. When our source explodes, it goes here, and it has some data information here, and reflected and receive this geophone. And we have a trace here. We can call this a common midpoint, and this trace includes lots of information about inside the earth. Just memorize this trace. We are going to talk about this trace in future. And also, as you see, some points we have more than one trace, some points. And if we combine these traces in just one trace, for example, if we have 40 traces in just one location, and we create one trace, we call this is our fault of this data. If we have 40 traces in one point, we have 40 faults. So it improves our seismic display, seismic quality. And this is the example of 3D seismic survey. The differences between 2D and 3D. In 2D, we have just one cable. This is the example of offshore acquisition. But in 3D acquisition, we have more than one cable. In this example, we have 4 cable. In this example, we have 8 cable. But in industry right now, we have 10, 16, and even 24 cables to acquire data. What is the benefit of this more cable? First of all, it is more cheaper because we have to cover this area in maybe 20 days by using 16 cables. But if you have 4 cables, it takes maybe a month or 2 months. And also, data quality is much better if you use more cable. I just want to show 3 different examples of this seismic surveys. The first example is coming from 1984. This is the 3D survey. And there is some acquisition parameters here. The second one is acquired 2000 after 16 years of this data. But this is 2D. After 4 years of this data acquired, this 3D high resolution data was acquired. And let's check some basic acquisition parameters, what we are going to deal with. Streamer length is 1 cable and 3000 meter length. In this survey, it's just 1 cable again, 1000 and 1500 meters cable length. But look at this 3D, it has 6 cables and 2400 cables. What is the important thing here? Let's compare this seismic quickly. I know maybe this is the first time you are going to see seismic, but I will show more examples. I just want to explain acquisition and interpretation relation. If you focus on this small area, this is 1984, this is 2000, and this is 2004. If you count this amplitudes, if you count this reflection, look at this black reflection is 1, 2, 3, 4, 5, 6 reflection in this area. But it says high resolution. What does it mean? If you count these black layers, 1, 2, 3, 4, 6, 5, 6, 7, 8, 9, 10, 11, 12, 13. There is too many information if we compare this data. And also, when we compare these two seismic, it also has pretty good resolution, but also it has some amplitude improvement. So we have different survey and we have different results, same area. And acquisition and interpretation relations. And before starting interpretation, you have to check and learn this about acquisition. First of all, if you design 2D or 3D survey, your survey direction must be perpendicular to your structure. Let's imagine this is your fault in map view. So these are your 2D lines. If these are your 2D lines, you have to acquire data in this direction. If you acquire in this direction, you cannot image this fault perfectly. And before you start interpretation, you have to ask you a question. How many 2D lines I'm going to deal with? What is the size of my 3D? What is my configuration of my survey? This is the example of my thesis dataset. This is from Gulf of Mexico. And this is our acquisition parameters. Look at the configuration of this 3D survey. It has 2 sources, the source, and 3 streamers. What is my record length? Look at here. My record length is 10.5 seconds. What is my receiver group interval? Do I have this information here? I don't know. This is every streamer has 240 hydrophone channel, and you have to check and learn this information. What is our fault size? What is our server acquisition datum? Let's move on. Some seismic processing example. We finished acquisition. Actually, we are going to talk about seismic interpretation maybe 1.5 hours. This is just beginning. But if you have a workshop about acquisition, maybe it takes more than 2 hours. So it's pretty large topics, but I just tried to cover basically again. Why do we need to process the seismic data? This is the basic seismic processing workflow, just main topics. This is the check format. We have to edit our data, determining parameters, main processing, migration, one of the most important things, weight processing, attribute analysis, and inversion. This is the example of stacked and migrated seismic section. Before migration, our reflections are not in correct location, in depth and also in X and Y coordinates. But after we migrate with correct velocity, if you focus on this area, we don't have any data here in stack section, but in migration, everything is in correct location. And after that slide, I will show some migration methods, different migration methods. This is Kirchhoff press-stack time migration. This is wave acquisition press-stack time migration. This is control beam press-stack time migration. In this three images, people try to image subsalt geology. As you see, the wave acquisition results in part B much better subsalt imaging compared to Kirchhoff. There is some uncontinuous reflection here. You cannot, they didn't image perfectly, but in this migration method, they image perfectly. And also maybe this control beam is much better than wave acquisition. There is some empty area here, but you can also follow this reflections as here. But it has some pros, but it also has some negative side effect about amplitude. So you have to understand what kind of migration did they use to process your seismic data. You have to check. And again, before you start interpretation, you have to learn your processing workflow, what kind of processed workflow they did to make better seismic. What is your aperture? What is your fault size, beam size, output record length? For example, maybe you remember I told it has 10.5 seconds record length in data, but output record length is 9 seconds. So there's 1.5 seconds a gap between them. Maybe because they didn't image the final 1.5 seconds, so they decided to cut this to spend less time to process. One of the most important things is polarity of data. So I'll try to cover more detail in my future presentation. And also, again, in migration, what kind of migration they used to process data. Seismic data display. Before computer-based seismic interpretation, people used paper-based seismic interpretation, but it is not as easy as right now, because you have just one big paper. You have to make it clear. You cannot spill coffee or turn your paper, and also you cannot zoom in or zoom out your seismic cross section. But right now we use computers. We use pretty good software to interpret seismic. So we can zoom in, zoom out. We can extract some amplitude map. We have pretty good. We have pretty good. How can I say? Abilities to use this software. Maybe you heard about SegWi data format. Before you interpret your data, you have to upload your SegWi format in your Petrel, Kingdom, or DSG software. I try to cover this right now. This is your SegWi format, your seismic SegWi format. In the SegWi format, we have binary line header. It is 400 bytes. Also, we have fstick header. it has lots of information about your seismic data. Also, we have lots of seismic trace under this binary header and APG header. This is our, again, seismic cross-section. As you see, we have lots of seismic trace. This is your seismic trace, and if you combine these seismic traces, you are going to have sorry, your seismic cross-section. And every seismic trace, if you are sample rate, let's say 4 milliseconds, every 4 milliseconds you are going to have 4 bytes data in your seismic cross section. Let's move on the next slide. This is the example of your APG header. If you don't have acquisition and processing parameters before you start interpretation, you can just check basically your APG header and binary header. What kind of information we are going to have in this APG header? For example, who is the client of this data? Who is the contractor? What is the sample rate? When did they acquire it? What is the format? We just talked about that SegWy. This is our SegWy format. What is the sample and trace? What is our data domain, time or depth? What is the number of cables and what is the length of this cable? We have just one cable and it is 10,050 meters. What is our shot interval? And also we can have some basic processing sequence here. What is our polarity? What is the polarity of our data? SEG normal polarity. And we have read on the multiple. We have phase and the bubbling, and lots of information you are going to learn in this APG header. It's pretty important. This is one of the most important things especially in oil industry. If you don't know your polarity of your seismic data, and you can pick wrong horizon, and it is meaningless if you don't know your polarity. And also, my question is going to about this data polarity, and we are going to find basically hydrocarbon in my question. Let's talk about North American polarity. North American polarity, the acquisition impedance is positive. The first peak is positive, then the output is negative. And in international polarity, the first peak is negative, and the output peak is positive. Maybe it doesn't make sense, but let's talk about real geology. This is onshore data. You can imagine this. This is the water, and this is sediment. If you go soft place to more harder place, and if you have North American polarity, you have this wiggle shape, positive. But if you have international polarity, you are going to have this negative wiggle. This is the real seismic again. As you see, this wiggle is, if our data polarity is North American, black is our positive data. So if this is our seabed, we can see this kind of image here. Let's talk about something. So if you know your data polarity, if your data polarity is North American, you can say this is your peak. But if you talk about international polarity, this is your trough. And also to find hydrocarbon, this kind of data, if your, again, polarity is North American, you have to go and check trough of trough amplitude to find hydrocarbon, and your top of your salt is going to be peak, and when you exit the salt basement of salt, you are going to see you have to pick your trough. Maybe we move real seismic data. It is going to be more clear. And let's talk about wiggles and color display. This is your variable. This is our variable wiggle display. As I explained, we acquired these traces. This is one of our traces, and it has some amplitude values. And let's talk about the amplitude values and how we can see in our seismic data. For example, in this wiggle, the amplitude value of this wiggle is 90. They create 100 and minus 100 amplitude values. And also, if you look at this trough, this is peak, this is trough, this is minus 85. And again, we have less amplitude values in this wiggle. It has 45. The value of this amplitude is 45. When we convert this wiggle to variable density area, we have this kind of picture. And what does it mean? If you have a dark blue, it means you have more amplitude values here, like 90. But it's getting light, so it means we have less amplitude values, 30, 20. And in white area, the amplitude values are 0. Again, if you are in your trough, we have minus amplitude values here, minus 85, dark red, and if we are in light red area, we have less amplitude values. And also, if we combine this wiggle and convert to variable density, we are going to deal with this seismic cross section. If you check this continuous blue area, you can see some dark blue area, some light blue area, and also in red amplitude values, we have some dark red area and some light red area, and between these amplitude values, we have some white areas. By interpreting these reflections, we can create some amplitude maps, and we can define some geological features. And let's move on how we calculate these amplitude values. Maybe you heard about this reflection coefficient. First of all, we acquire data. We have some impedance values. And by using this formula, we create reflection coefficient. Then we convolve this reflection coefficient with this our wavelet, and we are going to have seismic trace. And if we have loss of seismic trace, we are going to have seismic cross section. This is the example of sandstone, carbonate, and mine. Let's make this example. As you remember, we have some amplitude values in previous slides here. If we calculate this by using this formula, if we calculate our reflection coefficient, we find our amplitude values. This is minus 0.398. This is 0.437, and this is minus 0.259. If we convolve this reflection coefficient, we are going to have wiggle like this. So these are our amplitude values. So maybe you can make images in your mind when we have sandstone and carbonate, and if these are velocity and density values like this, we are going to have this kind of amplitude values. And when you combine these reflections, you are going to this interface between this different methodologies. Let's go some example of this wiggle and variable density display. As you see, this is a variable area with wiggle display. This is our reflections. We are going to interpret these reflections. If you put some variable density values, we are going to have this kind of visualization. We have lots of display techniques. This is a black and white. This is blue, red, white. This is black and white, and this is rainbow. This is black and white, and top of this black and white we have some wiggle. And, why do we have this kind of different display techniques? Because based on some experience, people understand that in this example, for example, in black and white data display is much better to show faults, some structural images. But if you look at this blue, white, and red, you are going to see amplitude values much better. Of course, this is based on people's experience, but you understand that you have lots of options to show your seismic data. Also, in our example, let me show here, we have just +1 and -1 amplitude values here, but in real data, we have 8 bits, 16 bits, and 30 bits data we are going to deal with. And what does it mean? If you have 8-bit seismic data, it means you have 256 possible values of amplitudes. So it means -128 to 127. But if you have 16-bit data in your seismic, it means you have 65,536 possible amplitude values. But if you have 32 bits data, it's too many numbers. I'm not going to rate, but you have pretty large range of amplitude values. It has some pros and some cons again. If you are going to deal with 8-bit data, for example, if your 8-bit data covers 8 GB data, if you improve this data to 16-bit, it takes 16 GB area. If you move 32 bits, it takes 32 GB area. Also, timing is pretty important. When you run some amplitude extraction, some volumetric, some volume attribute calculation, it takes some time. If you do some process by using this 8-bit data set, if it takes 2 minutes, and same data, if it is 16 bits, it takes 4 minutes. And if it is 32 bits, it takes 8 minutes. It's double itself to calculate some processing in your software. Let's talk about this question. I don't know we can answer this together or not. Maybe you can type. In our seismic data, let's say we have international polarity in this data. This is our international polarity. So the first peak is negative. So our red values is negative here. So if we find to hydrocarbon, or we want to relate it, we have to find hydrocarbon related reflection. Which one is going to our hydrocarbon related reflection? This white one, this red one, or this blue one? Maybe I can give you 30 minutes to answer this. You can type a meeting chat, or I can answer in 30 seconds. So if your first pick is like that, is red here, so hydrocarbon reflection should be reversed here. So maybe it doesn't work, but let me answer that. If you have international polarity in your seismic data and your color bar is red, blue, white, so it means you have your first pick is red. So you have to check reverse color. It means blue. If you are interpret this blue reflection, it may be related to hydrocarbon. So if you find to hydrocarbon, you have to pick this blue reflection. And as I told, we have some software to interpret seismic, and we have lots of benefits. These are same seismic cross sections, but it doesn't zoom in, so we cannot see lots of information. The zoom out section of this cross section. But if you vertically exaggerate, like let's say 4x, we have lots of information. We can see some faults here, some horizons, how they going through this direction to this direction, and we have some valve here. And also in this example, this is again zoom out section, pretty large 2D seismic cross section. But if you zoom in this red area, we can see clearly these faults, these reflections, and we can interpret more clearly. So you have options to zoom in and zoom out your seismic cross section. Some 2D seismic examples when we use 2D seismic data, and some 2D seismic data limitation I will show here. Let's talk about when we use 2D seismic data firstly. If you are in frontier area and if it is wildcat, you don't have any data in seismic data, but you want to find oil. You can acquire 2D seismic data. If you find some potential, you can make your 2D data set. You can acquire more data to understand area. After you decide, I want to drill a well and it is pretty potential area, then you can acquire 3D data. And also we use 2D data to tie two or more wells. For example, you have 3D data, or maybe sometimes you drill your well without 3D data, just using geology, field geology. But after you drill, you wanted to tie your well, you can acquire 2D data. But it has some limitation. As you see, this is 2D survey here. We have 2D line here, here, and also we have some large, big 2D line, but we don't have any information between these two lines, It's pretty large area. It is good to start to search this area, but it has limitation. We don't have lots of information in this empty area. Also, fault interpretation is pretty question marked by using 2D data. Let's say this is our map view. Like you are, just imagine yourself, you are looking at Google Map, as you saw some faults here, but if you have just 2D data set, you don't know these faults, how they relate to each other. It may be like this. This is your fault, or it can be your fault, or it can be your fault. You don't know if you have just 2D survey. But if you have 3D data, you have continuous data. Every 12.5 meters, you have seismic cross sections. So 3D seismic data provide continuous and throughout the survey area. Most of you are taking pictures, and when you buy a cell phone, you are talking about a pixel, a picture of pixel. In seismic data, we use voxel, equivalent of pixel, a picture element. So when we talk about these amplitude values, for example, in this wiggle has 90 amplitude values. So we store these amplitude values in this voxel. And also we put these amplitude values and store this 30 value in this voxel. Voxel is pretty much better than pixel, because when we zoom in and we don't lose any information, it's pretty strong visualization to interpret seismic. Also, 3D seismic has pretty advantages. When you look at your 3D survey area, you can go through your inline. Lots of inline you can check. You can visualize your seismic data in crossline. Also, you can create arbitrary line throughout your data, and also you can create some time slices. The weaver has complete freedom to pick the orientation of the lines being weaved. Unlike 2D grids, you have lots of advantages in 3D data. This is the workflow of synthetic seismogram. Sorry about this misspelling. Why we generate synthetics? Because our seismic data mostly in time domain, but our well data is in depth domain. So we have to tie our real geology to our seismic data. To do this, we use sonic log or VSP data, some velocity information here. Also, we use some density information. By using these two data, we create reflection coefficient, as we calculated previous slides. After we create this reflection coefficient, we convolve this data by using this violet. After this convolution, we have synthetic seismogram here. Now, this is our seismic trace. This is our synthetics, and this is again our seismic trace. But when we create our seismic synthetic seismogram, it doesn't in right location. What I try to say? Let's look at this is our seismic trace, seismic data, real data in time domain, but we create synthetic by using well information. But as you see, This analysis windows for when you check your cross correlation, it doesn't fit. There is too much information, too much reflection, but we don't have anything here. But when we shift this data here, we have pretty good correlation. So this reflection, these are has pretty good match. So we can say that this well data, for example, it is sandstone, it's related with this reflection. So we can call this reflections in a seismic time domain, it is sandstone. After we interpret the sandstone, we can create 3D distribution of this sandstone. Again, this is pretty basic. You just aware that we have to tie real geology to seismic. And as you know, I'm working on petroleum industry, so I'm going to show some hydrocarbon related structures example and some of my thesis examples. These are some simplified hydrocarbon traps. This is the fault. This is your oil where you store. And this is fault trap. And you also can find oil here. And this is combination fault and fault. We have some normal and district faults. And between them it's folding. And also oil can be accumulate here. Also, if it is salt and if it is sandstone, again, oil or hydrocarbon can be accumulate here. This is the example of faulted blocks. If let's say this is a normal fault, your sandstone is here and your sandstone is here, but there is no connection between them. So we can say it is. If we have hydrocarbon, it doesn't go through this impermeable shale. But when you move deeper part, this is permeable sand and this is permeable set. This is kind of your migration pathway. Your oil can move from this part to here. So you have to understand your fault interpretation and your geology. This is the uninterpreted seismic cross-section, and this is the interpreted cross-section. Just example, this is one of the example how people interpret seismic and how they visualize and how they show other people. As you see, there is lots of normal faults here, here, and there is some layer different reflection, different seismic responses here. This is pretty strong amplitude that they interpret as a different horizon here. And this is the visualization of normal faults at Egypt. They create their fault model. And again, before you start your interpretation, first you have to create your fault model. Then you can interpret your horizon based on this fault. This is just an example of visualization. And the boring part is my presentation is past. Maybe it's much better after that, because we are going to deal with the real seismic data. Maybe it makes more sense to you. First of all, I will show geology of my thesis study area. I will show some map, block diagram, and seismic cross-section. Then I will show basically, again, data acquisition and data processing parameters. I will show data polarity, and I will display my data, and we are going through this sub-information. Then we can interpret some faults and horizon in real seismic data by using Petrel software. This is one of the my surfaces from Gulf of Mexico. Actually, the background geology is in Gulf of Mexico. It's related to salt. We deal with salt tectonics in here. We have some mini basins here. We have lots of normal faults in my data set. Also, this is the block diagram of my study area during my thesis. After you finish your interpretation, your faults, your horizon, you can create this kind of block diagram to explain your study area. This is one of the example of north-south cross section here. This is map view. This is seismic cross section. As you see, we have lots of normal flows, normal faults related to this salt, and also I interpreted more than 6 or 7 horizons in this cross section. And this is another example. This is arbitrary line. As you see, I picked this arbitrary line through my seismic data. I'm free to pick this arbitrary line. Again, we have some listric faults, some synthetic of these listric faults, normal faults here, and lots of horizons. As I told you, we have to check acquisition and processing parameter before we start the interpret dataset. And let's check what kind of acquisition and processing parameters. We have 2 sources, 3 streamers, and we have 10.5 second record length. We have 48 faults. Just look at basic processing parameters. We have 3D Kirchhoff press-tag time migration. It performed in 2004. Again, we have 48 faults. Our output record length is 9 seconds, but when I interpreting my dataset, we trimmed our data 9 seconds to 6 seconds, that I will show you later. And let's talk about real seismic. In seismic interpretation part in real data, again, I will cover all of these topics. And let's move on Petrel software. Let me close this presentation. So I think you can see my screen again, right?
Yes, sir.
Yeah. Okay. First of all, let me introduce Petrel software. This is a Petrel. You have lots of tools, but we are not going to use everything in this presentation. Basically, we are going to use some seismic interpretation tools. When you click seismic interpretation, there's a new window here. It has manual interpretation, guided auto tracking, seeded 2D auto track, seeded 3D auto track. Lots of tools you can use. This is our map view. Let's move here. This is our map view. Right now we are in Gulf of Mexico. Let me turn on my GIS map here. As you see, this is United States of America, Gulf of Mexico. This is Louisiana. Our data set is offshore data. So I'm going to show some example here. Let me turn off this again. In this window, we have 2D seismic cross section here. We have another 2D seismic cross section. We can call one of them is inline, one of them is cross line. Also, we have some 3D window here. We can go through our data set in 3D. This is our inline, this is our cross line, and this is our time slice. You can zoom in and zoom out your data. Before we start interpretation, let's check our data polarity. As you see, this is a offshore data, so it means above 0, you have a water column. Let me know. 0 is your datum, your sea bottom. After this 0 value, it's time values, by the way, you are going to deal with water and some sediments. Let's check what is our data polarity. As you remember, we don't have any information about our acquisition and processing documents. We didn't see any information about polarity, but we can understand what is our data polarity. The first peak is blue here, and when we touch this blue reflection, there is some amplitude values here. Just focus on here. My mouse is here. As you see, the amplitude values is 288, and it's plus. If we move that, it is minus 90. So we can understand basically our data is North American polarity. The first peak is peak. So let's show something here. If you are looking at hydrocarbon, you have to pick your trough. It means your red reflections. First, let's look at how we can see our data in variable density and wiggle display and different color bar. This is our variable density display options, and when we right click in Petrel and touch this show wiggle, we can see wiggle, but it is not in the parameters right now. I hope I can find. If you zoom in, so we can see some our wiggles here. If I touch again, show wiggle and variable density, as you see, this is one of my reflection, and top of this my reflection is a wiggles. So when you one more time, this is just a variable density display options. So you can check your data both wiggle display, variable density, and you can mix both of them together. Also, when we talk about different colors, color bars, it is red, blue, and white. But also you can see your data black and white and rainbow. This is our color bar options. We have lots of options here. Let's look at black and white color bar. Black, gray, and white. Okay. Right now our data set is black and white. Also, you can change your color bar values to see much clear visualization. Let's make it 500 to 700. It's much better right now. And we can see faults here and some strong amplitude reflection here. So we can change our color bar. Let's go. We talk about rainbow. If we have rainbow here, it's kind of rainbow, sunbow. A different display of this data. People use different color bars to show different things. I have never used this color bar before. Just I want to show you. You have lots of options. So let's move on. Red, black, red, white, and blue. I like the visualization. Much better. As I told you, if you zoom in or zoom out too much your data, you cannot see clearly every geological feature. But in this kind of software, you can zoom in and zoom out easily. So you can go through your data without losing any visualization. As I told you about voxel things, you still have pretty clear image. How you zoom in, it doesn't matter how much you zoom in. So again, let's move this 3D visualization. This is our data. We can go through our X-line like this, and you can see the changing geology. You can follow it. You have this kind of options. And let's move on inline. These are just some of the options you can use in this kind of software. So let's move on the interpretation. Before you start interpretation, you have to interpret your faults in your study area, and you have to create your faults model. After that, you can start to interpret your horizons. It means your geological layers, reflections. To create these horizons, you have to create your ribbon map. I will explain what does it mean ribbon map. Then you can convert your ribbon map to surface. Let's try to interpret our seabed. Basically, first of all, I'm going to create some new horizon. It is seismic horizon 4. Let's name it water bottom. Our horizon name is water bottom right now. As we talk about this blue section, We have manual options. If you choose manual, you can pick whatever you want. But we have to use amplitude values. So because of that, we have to choose this guided auto tracking or seeded 2D auto tracking. If you choose this seeded auto tracking, if software can follow this horizon, this reflection, it will guide you. Let me also open map view. This is water bottom. Let's move 200 inline to the right, eastern part. As you see, this is our interpretation. You can see in map view. Let's move 200 meters, 200 inline eastern again. We are interpreting a horizon right now, water bottom horizon. And we are making our ribbon map. As you see, there is some gap because we didn't have any data here. So let me tell you how much area we covered by using this data set. I already create this polygon to cover this 3D area. As you see, this is blue polygon here. Let me calculate this the area of this polygon. It is 1,698 square kilometer area we are interpreting right now. This is the horizon interpretation, and we are creating the ribbon map right now. Before this session, I just interpreted water bottom. I think here. This is our ribbon map. When you finish your inline and crossline direction, you are going to have this ribbon map. After that, you can use software. By clicking this, you can see 3D auto track, and you can cover every empty space. And software is going to help you to interpret your data. But if you don't like your results, you can interpret more densely your ribbon map. You can create one more interpretation here, one more here, and one more here. You can make it as dense as possible, as dense as you want. After that, you can click here, make surface. You can create your surface by using this ribbon map. You can put your seismic horizon 3 here, and your boundary or polygon 3D survey area here, and you can get limits from selected here. And when you click apply, software is going to make a surface for you. It's already here, seismic horizon 3, our water bottom, and we interpreted our water bottom. This is in time domain. When you go through this map, again, if you focus here, water bottom is 136 milliseconds in this area. But if you go here, it is 183 milliseconds. It's much deeper, and it's more shallower here, 107 milliseconds here. let's make some fault interpretation, basically. Again, in seismic interpretation tool, you can create a fault. Here, interpret faults, create new faults, it's fault interpretation 2. And let's interpret this fault here. And let me turn on map view also. Let me turn off horizon, surface and horizon, and this is my faults. Let me decrease our increment. If we move here, again, too much increment. Again, my fault is still here. I can see that. One more move or other direction. My fault is still here. And after I finished, I will show in 3D view how can we observe, how can we visualize this faults. Let's check in 3D view, and this is our 3D map. And let me turn on. This is my time slice, and I'm going to turn on my faults. As you see, this is my fault plane. We just interpreted a fault. If we go through this inline through the faults, this is our fault in seismic. Also in time slice, you can observe the end of or bottom line of this fault. And thank you very much. It is pretty small amount of time to explain seismic interpretation. Actually, I try to cover just basic things, how we acquire data, how we process data, how we visualize data, seismic data, and how we interpret seismic data. I try to cover everything basically. I hope it helps. And if you have any question, I like to help you in future. You can communicate with me in LinkedIn. And thank you very much. This is the end of my presentation.
Thank you, sir. Thank you so much. The session is now open for questions. Attendees are requested to send their questions in the chat box on their screens.
Okay. Let me answer the first question. Yes, it's possible to investigate very shallow depths by the seismic reflection method, especially in onshore data. Let me show the example. This is your source, and this is your receivers on top of the earth. So you can image maybe 10 meters, 10 meters, 12 meters depth of subsurface. So it's possible. I hope this is your answer. What are the differences between seismic structure interpretation and seismic processing? Let me explain again. First of all, we acquire some seismic data. We have source, we have receivers. After that, after we acquire data, we have some stack seismic cross-section. After we process this stack section, there is too much processing steps. We have final processed seismic cross-section. This seismic cross-section is ready to interpret. After we interpret these horizons, faults, some geology, we have interpreted seismic cross-section. So processing is a step after acquisition. So let me show again an example of seismic cross-section. Yes, this is a process seismic cross-section without interpretation. We have to process seismic data to put reflection the right location, basically. After we have in right location, we can interpret seismic data easily. Thank you very much, Selim.
Any other questions?
Static correction. Just like processing does interpreters as a structured, structured workflow to what we need to first interpret. Let me show the seismic interpretation workflow. I think it's the beginning of my set. Yeah, this is the basic workflow for seismic interpretation. This is your second question. If you, first of all, you have to define your purpose. Then you acquire your data, if it helps you. Then you create your common data database, seismic, well, and other data set like geology, magnetics. After that, you have to tie your seismic data. Then you have to make your structural interpretation, stratigraphic interpretation, then rock properties. This is your basic workflow. You have to start first. You have to start with faults. Then you can go to your horizons, and you can create your model, structural model. You can start like that. We need static correction. It's pretty actually complicated question, but actually I had slides, but then I take it off. But in Earth, it basically in Earth it is not as flat as is in the sketch. We have some mountains, we have some hole here, something like that. When you acquire data, there is some elevation differences. To correct these elevation differences, we have to make static correction. It's basically something like that. Pretty actually large topics. You mentioned about cutting record length. If a data with 9 seconds record length is cut to 6 seconds and passed to query, wouldn't that affect deep section interpretation? Yes, actually it affects in the depth section, but I think, let me show this cross section. This is the data we are talking about. As you see, this is sorry. This is 9 seconds, 6 seconds. But as you see, after 4.5 seconds or 5 seconds below data, we don't have any information. So to process more quickly, and also it's basically to process more quickly, they cut data after 9 seconds to process. And also in my data, because we don't have too much space at that time, we cut our data set after 6 seconds to visualize, to create some attributes more easily. If you don't mind, please post the link again. I didn't see. On the third question, that only applied on shallow water data right now. Okay. Actually, it depends on the basin. If your sediment thickness is more than 12 seconds, if you have some data, you don't need to cut your record. You can see everything. For example, let me show here. In this data, again, this is 6 seconds, but you also have lots of reflection here because it is not related to salt tectonics. You can image everything here. So you don't need to cut. It depends on your basin and your sediment thickness, actually.
I hope there are no more questions, sir.
Okay.
We extend our most profound appreciation to you, sir, for such an illuminating, instructive, and engaging sessions. And the destinations that we adapted today have surely fortified our insight.
And thank you very much. It's pretty hard to cover everything in just two hours. So maybe it's too complicated, too complex to understand in the first time, but I hope you have some awareness right now what is seismic data, how we can visualize. I hope it helps.
Yes,
thank
sir,
you very much for your
May
listening.
I now invite Mr. Aditya Singh Pal, Quality Assurance Officer, UPES AAPG Student Chapter, to give the vote of thanks.
Greetings, everyone. Thank you, Shivaji, for asking me to deliver a vote of thanks. On behalf of UPES AAPG Student Chapter, I would like to express sincere gratitude to our esteemed Mr. Ozbil Yapar, sir, for sharing such an impactful knowledge with us today. This enlightening workshop under the banner of APG Pinnacle Series has rendered us with great insights today. I would also like to thank entire team of UPES AAPG Student Chapter and MOC for organizing such a flawless workshop. And finally, my sincere thanks to such a wonderful audience who attended the workshop and made this great. Thank you, one. Thank you all.
Thank you, sir. The workshop session is now concluded. Once again, a big thanks to you, sir, for your precious time and such valuable experience. Also, I would like to thank you all for coming here and for such undivided attention. Thank you so much.
Thank you very much.